I've got here a slinky, and I'm gonna send a wave down the length of the slinky by pushing it inwards like that. And now I have a question for you. How can I make that wave move faster down the slinky? I'm going to intuit that a lot of you probably guessed you push harder, so let's check it out. No. No matter how hard I push, the wave still moves the same speed down the length of the slinky. So what else could I do? Well, I could change the medium. I could change the slinky by stretching it out even more. I've got more on either end, so it's a little more stretched out. Check it out now. You can't even see how fast the wave moves down the end. It's like immediate. So hopefully by the end of this lesson, we're gonna understand why that works. Hey, I'm Dianna Cowern and welcome to lesson 17 of Physics by Dianna. I usually call this Dianna's Intro Physics class because it's useful if you're looking for an overview of intro-level physics topics from kinematics to energy to electricity. But this series is also useful if you're looking for a review of the AP Physics 1 curriculum, which is what we follow. Okay, so today's lesson. Today is about waves and light and sound, which are all related things. If you're seeing or hearing this video, it's because light and sound waves are reaching you from your screen or from your speakers. So waves can form in and travel through materials like water, which is the reason that surfing exists. So thank you, waves. So our theme today is catching waves. I couldn't fit my whole surfboard in the studio, so just dress up. So what is a wave? I'm going to talk about some misconceptions about waves and about what waves are. So let's use the slinky again. So if I shoot a pulse down the length of the slinky, like I did before, that's a type of wave. Notice that the slinky itself doesn't travel in the direction that the energy does. This is not a wave. For a wave to happen, the slinky bunches up and then that bunching moves down, but it returns to its original state. So even though it looks like something is moving down the length of the slinky, no thing actually is moving. It's just a disturbance traveling down. Same with waves in the ocean. They keep coming at you, they keep crashing on shore, but it's not the water continually coming at you, or you would get continually rising seas. So unless a tide is happening, the water is not moving up at you. It's just this disturbance in the water moving forward. If you do a cannonball into a pool or throw a rock into a lake, then when the ripple forms, energy is moving through the water in the form of a disturbance. But if you look closely at the water itself, you see every part of the water moves up and down, or maybe with some circular motion, but it doesn't travel outward like the ripple does. It is energy that's moving outward, and this disturbance transmitted down the wave. Now we can easily define what a wave is. It's a disturbance or a displacement of some medium that carries energy. That's a wave. Here's a crazy type of wave, a gravitational wave. We've talked about them before, but it's the same concept we just discussed. Some disturbance happens, like two black holes collide, and that triggers the stretching and compressing of space-time itself. It's like the ultimate medium for waves to go through. And of course, it definitely carries a lot of energy. If you took all of the mass of 3 suns and turned it all into energy, that's how much energy some of these collisions have released. So crazy. Lucky for us though, that energy is not concentrated right on us. It spreads out, and typically the collisions happen very far away. Now there's a couple different ways I could have sent a wave down this slinky, even though it's just a simple piece of plastic. The way that I just did it was by pushing along the slinky, but I could have also moved it side to side. See how those are different? So the first one is called a longitudinal wave, where the individual bits of the medium move back and forth along the direction that the energy travels. So that's a longitudinal wave. That's how sound waves travel, through air. So when I yell, Stella! So when I do that, I'm compressing the air, and then parts compress and parts stretch out, and that compression moves through the air toward your ear. But if you look closely at the individual particles, they're just moving back and forth. Now, the other way of making a wave, that up and down motion, that's called a transverse wave. I like to remember it Longitudinal is along the direction, and transverse is the other one. In the transverse case, the medium moves perpendicular to the direction that energy travels. Interestingly, that's how light works. Light travels as a transverse wave, disturbing the electromagnetic field. Yeah, we're gonna get to that weird concept a little more in the next lesson, but here's a mathematical representation of light waves disturbing the electromagnetic field. So the wave, that's a transverse wave. You could make it a longitudinal wave, but everyone would have to go like this. Fun fact, some waves are actually a combination of longitudinal and transverse. The water wave animation that we saw before is just like that. A little bit of back and forth, a little up and down, and the result is a circular motion. Okay, waves. But what can we, as physicists, do with them? Well, obviously we measure things, like measuring the energy carried by a wave. Let me tell you, it's not easy to just look at a wave and know how much energy it's carrying. But there are other properties of waves that we can more easily measure and use those to figure out the energy. And each of those properties is important in its own way too, as I'll explain. Consider a transverse wave like a slinky oscillating side to side like this. I'm gonna draw that. So what I'm drawing is a little snapshot of the wave in time. So the wave has some properties that are familiar from previous videos. As a part of the slinky moves side to side, it takes some amount of time to return to its starting point. So that would be like the wave going from here to here to here. And that time it takes is the period of the wave. Time is the period. The period is something that surfers care about because it tells you how often the waves are going to come. If we measure how many oscillations happen per second, like the frequency of the waves, that's called the frequency. And just like when we talked about angular motion and simple harmonic motion, the frequency is inversely proportional to the period. So T equals 1 over F. And we can work out the units of this too. So the units of period are obviously a unit of time, seconds, and that's 1 over the units of frequency are hertz. Hertz is actually 1 over seconds, so if you flip that, you get seconds back. Musicians or audio people very much care about frequency because for sound waves, the frequency is what determines the pitch of a note. The higher the frequency, the higher the note. Check it out. I've got this app that shows you sound waves live. Actually, it might be a little easier to see what I'm talking about if you know the next property called wavelength. That's the distance between two peaks of the wave, or two troughs, or two midpoints. Not these two midpoints, it's like a full wavelength. Basically the distance between two identical points on the wave. Lower notes have longer wavelengths, and higher notes have shorter wavelengths. Physicists use the symbol lambda for wavelength. There's one more useful property of waves that we're not really going to use today, but you might as well know. It's called the amplitude, and it's basically the midpoint. It's like where the slinky would be if it were resting, all the way up to the top or up to the bottom, same distance. So this distance and this distance, those are both amplitude. Wavelength is also super important because it's how physicists describe colors of light. For example, the wavelength of blue light is around 470 nanometers, which is shorter than red light, which ranges around 750 nanometers. And then beyond that, on both ends of the visible spectrum, well, we don't talk about that. Just kidding. We're going to get to that in the next lesson. But I'll give you a hint. Even though we can't see some wavelengths of light with our eyes, astrophysicists use different kinds of telescopes and detectors to be able to collect light of all different sorts of wavelengths so we can learn extra things about stars and galaxies that we otherwise wouldn't be able to see. And on the topic of wavelengths, with our slinky, we can see that if we oscillate this slinky with quick little waves, or like this, we're sending more energy down with the wave than if you oscillate with longer waves. Obviously, more energy. And that's true for light as well. light with shorter wavelengths carries more energy than light with longer wavelengths. That's why ultraviolet light, which has really, really short wavelength from the sun, can damage your skin because it carries even more energy than blue light or than any of the other visible colors of light. Fun fact, humans can't see ultraviolet light, but some other animals can. There are butterflies, fish, even reindeer that can see ultraviolet light. Flowers look different in ultraviolet light to attract pollinating insects. So there's a specific relationship between the frequency and the wavelength of a wave, and we can figure this out with our slinky. So I'm going to move the slinky in two different ways, a long wave and a short wave, and then measure their wavelengths and frequencies. This one's about 0.5 meter and about 0.5 hertz, and then this one's about 0.1 meters and 2.5 hertz. So let's write that down. The wavelength of my longer wave was 0.5 meters, and my frequency was 0.5 hertz, about half a wave per second. And then my second one was 0.1 meters, the faster one, and the hertz were obviously quicker at 2.5 hertz. This makes sense? Longer wavelengths happen less often, shorter wavelengths happen more often. Now watch what happens when I multiply the wavelength and the frequency of these two waves. If I multiply these two, I get 0.25 meters per second. And if I multiply these, I also get 0.25 meters per second. Interesting. I got the same number. So what this number is the speed of the wave traveling through the slinky, or v. So I can now write down this relationship. Velocity of a wave through a medium equals the wavelength times the frequency of the wave. We call this relationship the wave equation, and it's true for all waves. And we can use it to figure out all sorts of things. Like, how long are the waves that carry music from your radio station to your car? Here we would use, for v, we would use c, because that's the speed of the wave. The speed of the radio wave is the speed of light, because radio waves are light. So we would use c for the speed of light, which is about 3.00 times 10 to the 8 meters per second. You already know the frequency. You maybe didn't know you knew, but the frequency of your radio station is just the dial number. So mine from my favorite radio station growing up was 93.5 on the dial. And what that means is 93.5 megahertz. So 93.5 times 10 to the 6 hertz. And so I can use this equation, 3.00 times 10 to the 8 meters per second equals my wavelength, which I want to find out, times my frequency, which is 93.5 times 10 to the 6 hertz. So my wavelength is 3.21 meters. 3.21 meters. That's huge. That's why antennas are big. I love to think about these huge, long light waves traveling through the air and then getting snagged by my car's radio antenna, also that I can rock out. All of those radio telescopes that you've ever seen, they're massive dishes because they have to pick up these wavelengths that are huge. And we've used these radio telescopes to detect light waves from an outer space in order to study pulsars and exoplanets and even search for extraterrestrial life. Okay, let's talk about the speed of waves, because I feel like we're almost to the point of answering the question from the very beginning. Let's talk about the speed of sound. The speed of sound depends on a lot of things, and I think you've seen this demo before. I'm gonna get to it. Sound travels through solids faster than it does through gases, for example, because the molecules are more tightly bound together. So you can put your ear down and hear an earthquake before you heard it in the air. Can you hear earthquakes in the air? I don't know, maybe. The molecules are bound together more tightly in the ground, which affects how fast particles can hit each other and transmit the waves. Which is why in gases, I'm getting to the demo, the speed of sound depends on the mass of the molecules and the temperature of the gas. So let's think about two different gases. A really light one like helium and a really heavy one like sulfur hexafluoride. My friend Mark Rober did an awesome live streamed physics course, and he did this demo during the course.
Because this is sulfur hexafluoride, it actually does the opposite of helium. It makes your voice low. So we're gonna discuss that. And here it starts to wear off. It's like still in my lungs. Why does sulfur hexafluoride make your voice go really low?
And yet helium makes it go really hot. What the heck is going on there?
I would someday Love to try that, but thank you in the meantime, Mark. You should go check out his course. So the little helium molecules are easier to move around than the big, heavy sulfur hexafluoride molecules. So therefore, sound travels faster in the helium gas. And if you look at our wave equation, velocity equals lambda times frequency, well, a faster velocity traveling faster through those light molecules means V goes up, means my frequency goes up. Frequency goes up, pitch goes up. That's why when someone talks after inhaling helium with that faster velocity, their voice becomes higher pitched with the higher frequency. And if you inhale sulfur hexafluoride, then velocity goes down, frequency goes down. Your voice would sound lower pitched.
It actually does the opposite of helium.
So the speed of sound really depends on the type of material. And we can use that now to explain our Slinky demo. I know it seems like the same material, the same medium. So we're actually changing the medium when we stretch out the Slinky loops. We're putting it under tension, and that changes the medium. This is how sensitive waves are to the medium that they're traveling through. Just by stretching it out, I can change the speed of waves inside the Slinky. Very cool. So let's go back to light waves. You've probably heard that the speed of light is constant. That's not quite 100% correct. In order to be totally accurate, we need to say the speed of light in a vacuum is constant. In a vacuum, the speed of light is C equals 299,792,458 meters per second. By the way, this is also the speed of gravity. Think about that. So this is about 3 times 10 to the 8 meters per second. I'm gonna take a short detour and do a quick little problem. So sound is a lot slower than light, and now you know it would depend on what elevation you're at, how hot it is out, but typically sound travels at about 343 meters per second. You can see now these are a lot different in magnitude. So sometimes we talk about how you see lightning before you hear it, but let's talk about a rocket launch. If you're ever lucky enough to go see one, someday, I hope, then say you're standing 11 kilometers away, so that's your distance away. 11 kilometers, that's 11,000 meters. So say my distance is 1.1 times 10 to the 4 meters. I want to know how long it would be between when you see the ignition and you hear the rumble. Okay, so I'm going to use an equation from our early kinematics lessons. Velocity equals distance per time. My distance is 11 kilometers, and I want to know my time. So for sound, that's going to be, bring the T up, bring the V down, so I'm going to divide distance by velocity. So I'm going to have my 1.10 times 10 to the 4th meters over my velocity. And for sound, that's 343 meters per second. That equals 32.1 seconds. That's a long time. And then for my light, same distance, but much bigger velocity. I'm using 3 significant figures. So 3.00 times 10 to the 8 meters per second. And I get 0.00004 seconds. So if we subtract these out, you just get that 32.1 seconds. So you would see the ignition half a minute earlier than you would hear the rumble. That is cool. Coming back to what we were saying about the speed of light in a vacuum, but light actually slows down when it travels through matter. So light traveling through Earth's atmosphere travels a tiny bit slower than light in outer space. And if light enters a denser medium like glass or water, it slows down even more. So what happens when light slows down? So let's say light is traveling through air and it hits water. The light slows down in the water and it bends, it changes direction. That's one of the weird results of light changing speed. This bending of light is called refraction. And you've probably seen light refracted if you put a spoon or a straw into a glass of water. It looks like the spoon is bent at the surface of the water because of refraction. We actually did a video where I took a straw and I put it into the water and then looked into the straw, moved it up and down, and you can see the image at the bottom getting blown up into this big image and then shrinking way far down as you bend the surface of the water at the top. This is actually how lenses work. They are designed to bend and refocus light to different parts of your eyes as the light enters either a glass lens or a plastic lens or even a water lens. So you get a sharper image. Cool. So all sorts of cool things happen when waves interact with matter. Another example is the Doppler effect.
The 3 remaining cars take the checkered flag, thus ending what must be counted as one of the most astounding performances in automobile history.
So say the source of your light waves or your sound waves is moving toward or away from you. So you know what it sounds like when a parked fire truck has its sirens blaring. It's emitting these sound waves with a certain wavelength. But now imagine that the fire truck is driving toward you. So then between each peak in the sound waves it emits, the truck gets a little bit closer. So that means overall the waves are going to get squished together to a shorter wavelength. And if the wavelength goes down, that means the frequency goes up. So it sounds higher pitched as it comes toward you. When the fire truck passes you, the opposite is happening. As the truck moves away, the wavelength gets longer and spread out between these peaks. The wave is emitted, truck moves away, the next peak is emitted. And it becomes lower pitched as it's moving away. So this is called the Doppler Effect. Waves getting shorter or longer because the source is moving toward or away from you. And you can hear it change as it goes by, that meow. So maybe you can figure out why you never hear meow. Intriguing. Now what if the moving object is emitting light waves, like a star? So if a star is moving toward us, its light waves actually get squished into shorter wavelengths, which means, what does it mean for the color? It means it gets bluer. And if it's moving away, then same thing. The light wave gets stretched to longer, redder wavelengths of light. So it gets redder. And we call that redshift and blueshift. You can understand the joke on the bumper sticker my high school physics teacher had on his car that said, it was a red sticker, and it said, if this sticker is blue, you are traveling too fast. Whew, wow. We just did a lot. Whew. All with a few simple ideas about relating the wavelength and frequency of waves to their speed. And we've just barely scratched the surface. We didn't even get to reflection of light. Sometimes light doesn't go into the surface, it reflects off. That's called reflection. And we've also got transmission, where light waves go through the medium. There's diffraction and dispersion and standing waves, which are super cool. There's the physics of music. We just don't have time to cover all of this. But that's the great part about physics, because the more you learn, the more you realize you have yet to understand. So that's our lesson today on waves, light, and sound. When I ask you what you learned on YouTube today, here are your key takeaways, or should I say takeaways. Number 1, waves carry energy and information, and they're defined as transverse and longitudinal. And number 2, V equals lambda times F. The speed of a wave is equal to its wavelength times its frequency. And here are all the problems that we solved in today's lesson so that you can go solve them on your own, because solving problems is a super important part of learning and understanding physics. And one last thing, one really cool little bit of physics history actually. Stick around for this. This is pretty mind-blowing. In the 1910s and 1920s, astronomers measured the Doppler shift of objects that they called spiral nebulae, which were these weird fuzzy patches of light in the sky with spiral patterns that they assumed were inside of the Milky Way. But it turns out that a lot of these objects had longer, redder wavelengths than they should have had, meaning now you know that they were moving away from us. Astronomers measured the distances to these spiral nebulae and figured out that they were not in the Milky Way, they were actually their own galaxies. And the further away a galaxy was, it turned out the faster it appeared to be moving away. Now we know why. We know it's because the entire universe is expanding, and galaxies and galaxy clusters are moving apart from one another because of that expansion. That's why all these galaxies appear to be moving away. We don't know why the universe is expanding. What we do know is that there's some source of energy we don't quite understand that's making the universe expand faster and faster, and we call that energy dark energy. Super cool stuff. And if you continue on with physics and take a class in, say, cosmology, you get to learn a lot more about dark energy and this crazy type of physics. That's it. And now for a message from a special guest.
Hey, what's going on? My name is Destin Sandlin. I'm a mechanical and aerospace engineer, and I love physics. So I was super excited to learn that you are learning physics with Dianna, and I want to encourage you, because for me, physics is like this storybook. Like, you get more and more understanding about the world around you as you peel back the pages of the story. But the cool thing is, the more understanding you get, the more there is to understand. Like, you can go deeper and deeper and deeper, and I just love it. So I am super excited that you're studying with Dianna, and I would like to encourage you to just go as far as you can with it. Anyway, nice to meet you. My name is Destin, and I hope you fall in love with physics.